The morning of March 23, 1945. Lieutenant Colonel David Pergrin stood on the east bank of the Rhine River at Remagen, Germany, watching American engineers work a miracle that military doctrine said was impossible. 48 hours earlier, the Ludendorff Bridge, the only intact Rhine crossing for 300 kilometers, had collapsed into the river, killing 28 engineers and trapping the US First Army's entire spearhead on the wrong side of Germany's last natural barrier. General Courtney Hodges had maybe 72 hours before German panzer reserves counterattacked. Standard pontoon bridge doctrine required 3 days minimum for a crossing this wide. Pergrin's battalion needed to do it in 90 minutes, or watch the most important breakthrough of the war die at the water's edge. This wasn't an isolated crisis. Across every theatre of World War II, rivers defined the tempo of operations more than any weapon system. The Seine, the Po, the Volga, the Irrawaddy. These weren't just blue lines on maps. They were liquid frontiers that transformed offensive momentum into static vulnerability. In September 1944, when Patton's Third Army reached the Moselle River near Metz, French resistance fighters had identified 12 intact bridges suitable for armour. By the time American spearheads arrived, Wehrmacht engineers had demolished all 12. Patton's advance stopped cold for 11 days, while engineers assembled traditional pontoon bridges using equipment designed in 1938. The mathematics of river crossing under fire were brutally simple and universally ignored by peacetime planners. A mechanized infantry division moving at combat tempo needed to push 15,000 men, 4,000 vehicles, and 800 tons of supplies across a river in under 18 hours to prevent German forces from establishing defensive positions on high ground beyond the far bank. Every hour of delay multiplied casualties exponentially. The US Army's own 1944 analysis calculated that each additional hour spent bridging a contested river increased infantry casualties by 7% during the subsequent breakout operation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Traditional military pontoon bridges traced their conceptual roots to technology that hadn't fundamentally evolved since Roman engineers floated timber platforms across the Rhine in 55 BC. The Allied armies of 1944 still used pneumatic rubber pontoons, essentially giant reinforced inner tubes that required manual inflation, careful placement by crane, and constant adjustment as water levels changed. A standard M1942 pontoon bridge across a 200-foot river required 48 individual pontoons, each weighing 800 pounds when inflated, connected by steel treadway sections that weighed another 400 pounds each. Assembly demanded specialized equipment, heavy cranes, winches, anchor cables, and an engineering company of 200 men working in shifts. Under ideal conditions, with no enemy interference, calm water, and experienced crews, construction took 36 to 48 hours. Under combat conditions, those times doubled. The German Wehrmacht knew this arithmetic intimately. Their doctrine for river defense assumed Allied engineering battalions needed at least 2 full days to bridge any waterway wider than 150 feet. This gave defending forces 48 hours to position artillery, sight machine gun nests, pre-register mortar coordinates, and mine the approaches to probable bridge sites. River crossings weren't tactical problems, they were massacres waiting to happen. The British learned this lesson in blood during Operation Market Garden in September 1944, when XXX Corps attempted to bridge the Waal River at Nijmegen to relieve paratroopers at Arnhem. German 88mm guns hidden in buildings on the far bank destroyed 3 pontoon bridges before engineers could complete the far bank connection. The crossings took 4 days instead of 1, and by the time XXX Corps finally pushed across, the Arnhem pocket had been overrun. Post-action analysis by British Second Army headquarters concluded that if pontoon bridge assembly time could be reduced by half, the entire Arnhem operation might have succeeded. Soviet forces on the Eastern Front faced identical challenges on an even more devastating scale. When the Red Army reached the Dnieper River in September 1943, they found a waterway stretching up to 3 kilometers wide in places, With every bridge demolished and German artillery commanding every obvious crossing site, Stalin's order was characteristically blunt: cross within 1 week or lose the initiative. Soviet engineers attempted crossings using every available piece of equipment: wooden boats, captured German pontoons, improvised rafts lashed together from oil drums and timber. The result was catastrophic. 23,000 Soviet soldiers died in 2 weeks, attempting to ford the Dnieper or cross on makeshift bridges that collapsed under the weight of 34 tanks. The problem wasn't courage or determination, it was engineering physics. Water is extraordinarily heavy. Every cubic meter weighs 1,000 kilograms, which means a pontoon bridge spanning 200 feet of river, that's 30 meters wide and 3 meters deep, must displace over 3,000 cubic meters of water to support a single Sherman tank crossing. That requires either enormous pontoons, which are impossible to handle manually, or many smaller pontoons precisely placed and securely connected, which takes time. Time that soldiers pinned on hostile riverbanks didn't have. Allied intelligence estimated that Wehrmacht engineers had pre-wired more than 2,000 bridges between the Atlantic Wall and Berlin for demolition. Every major river from the Seine to the Elbe would become a choke point, where the side that could bridge faster would control the war's tempo. By late 1944, it was clear that whoever solved the pontoon problem would determine whether the war ended in 1945 or dragged into 1946. The existing technology wasn't just slow, it was obsolete for modern mechanized warfare. Someone needed to rethink the entire concept from first principles. In November 1944, that someone wasn't a decorated military engineer or a research scientist at a prestigious university. He was a civilian construction foreman from Tulsa, Oklahoma, who'd spent the last decade building oil drilling platforms in swamps and had a radical idea that military engineers considered borderline insane. John Wesley Steinman wasn't supposed to be anywhere near a war zone. Born in 1903 in Muskogee, Oklahoma, he'd spent his career in the unglamorous world of civil engineering, primarily building temporary bridges for oil companies, drilling in the waterlogged regions of eastern Oklahoma and northern Louisiana. While prestigious firms designed elegant steel spans for major cities, Steinman figured out how to throw a functional bridge across a creek in 6 hours, using whatever materials were cheapest and available. His specialty was speed and economy, getting equipment to drill sites before competitors did. The work gave him an intuitive grasp of buoyancy, structural loading, and improvisation that textbook engineers lacked. Oil rigs don't wait for perfect conditions. If your pontoon sinks, you lose the contract. If your bridge can't handle a 15-ton drilling rig, the company goes elsewhere. Steinman learned to build fast, build light, and build reliable. By 1941, he ran a small engineering firm with 12 employees and a reputation for solving problems that sounded impossible right up until he solved them. Steinman's involvement with military engineering came entirely by accident. In August 1944, the Army Corps of Engineers issued a public contract request for civilian consultants to evaluate pontoon bridge designs. The Corps was drowning in complaints from field units about existing equipment: too heavy, too slow to deploy, too prone to failure under combat stress. They wanted fresh perspectives from people who built bridges for a living, not for theory. Steinman's firm was small enough to be desperate for government contracts and desperate enough to bid on anything that paid. His proposal landed on a desk at Corps headquarters in September. Most submissions offered incremental improvements: lighter materials, better connections, refined inflation systems. Steinman's proposal suggested throwing out the entire pneumatic pontoon concept and replacing it with something that sounded like a joke: hollow steel boxes welded from quarter-inch plate, filled with foam, and designed to clip together like toy blocks. The initial engineering review dismissed it in 2 sentences: solid pontoons, too heavy for field deployment; foam insufficient for redundancy if hulls breached. Steinman's response, preserved in Corps archives, was characteristically blunt. Your current pontoons weigh 800 pounds each and take 20 minutes to inflate per unit. My boxes weigh 700 pounds, require zero inflation, and if one gets hold, the foam keeps it floating while the crew keeps building. You want faster bridging or prettier paperwork? The Corps invited him to Fort Belvoir, Virginia, in October, mostly to explain in person why his idea violated basic engineering principles. He arrived with a prototype. The demonstration at Fort Belvoir became legendary among military engineers who witnessed it. Steinman had built a 1/5 scale model of his pontoon system, hollow steel boxes, 12 inches wide, 18 inches long, 8 inches deep, filled with expanded cork foam and connected by simple steel pins that dropped through aligned holes. Each box could be handled by one man. The connections required no tools, just alignment and gravity. The Corps engineers set up the standard test. Float the model in a test tank, load it with scale weight equivalent to a Sherman tank, and measure deflection and stability. Steinman's model floated the test load with less than 1 inch of deflection. Then he asked the observers to shoot a hole through one of the boxes with a .45 caliber pistol. The box flooded, but the foam kept enough buoyancy that the bridge section remained stable. Then he removed the damaged box by pulling a single pin and slid in a replacement in under 30 seconds. The Corps engineers requested a full-scale prototype immediately. What Steinman had invented wasn't particularly sophisticated from a pure physics standpoint. It was clever application of principles that civilian bridge builders used routinely, but military engineers had ignored. Hollow steel construction was lighter and stronger than pneumatic rubber. Closed-cell foam provided redundancy that air chambers couldn't match. If you puncture an inflatable pontoon, it sinks. If you puncture a foam-filled box, it loses maybe 20% of its buoyancy. The clip-together connection system eliminated the need for skilled labor or specialized tools. Any soldier who could align 2 holes and drop a pin could assemble the bridge. The real genius was in the manufacturing tolerances. Steinman designed the boxes to be welded from flat steel plate by semi-skilled workers using standard equipment. No complex curves, no precision machining, just straight welds and right angles. This meant production could scale rapidly, using existing industrial capacity without retooling entire factories. Cost per unit, $47 in raw materials and labor, compared to $123 for a standard M1942 pneumatic pontoon. By December 1944, the Corps had authorized production of 500 prototype units for field testing. The first shipment arrived at Antwerp, Belgium, in late January 1945, consigned to the First Army's engineering depot. Exactly 67 days before they would determine whether the Rhine crossing at Remagen succeeded or failed. The Ludendorff Bridge collapsed at 3:07 p.m. on March 17, 1945. Lieutenant Colonel Pergrin's 291st Engineer Combat Battalion had been working on the captured bridge for 10 straight days, reinforcing its damaged spans and clearing German demolition charges that Wehrmacht engineers had tried to detonate during the initial capture. The bridge had been struck repeatedly by German artillery and V-2 rockets attempting to destroy it. Structural steel that had been stressed beyond design limits for nearly 2 weeks finally gave up. 28 American engineers died in the collapse, buried under twisted girders or drowned in the Rhine's swift current. Worse than the casualties was the strategic crisis. The First Army's entire spearhead, 3 infantry divisions and 2 armored combat commands, approximately 75,000 men with their vehicles and equipment, sat on the east bank with no way to receive reinforcements or supplies except by small boats and improvised ferries. German forces were already massing for counterattacks designed to crush the bridgehead and throw American forces back across the Rhine. General Hodges needed a bridge, immediately, capable of handling Sherman tanks and supply trucks in continuous flow. His operations staff calculated that maintaining the bridgehead required moving 400 tons of ammunition, fuel, and rations across the Rhine every 24 hours. That demanded a Class 40 bridge military designation for a span capable of supporting vehicles, weighing up to 40 tons spaced no closer than 60 feet apart. Standard Corps doctrine for a Class 40 pontoon bridge across a Rhine crossing at Remagen required assembling a span 430 feet long, using 86 M1942 pneumatic pontoons. The First Army Engineering Depot at Antwerp had the necessary pontoons in stock. What they didn't have was time. Even under ideal conditions, with experienced crews and no interference, assembly would take 72 hours minimum. Pergrin's options were severely limited. He could attempt the standard pneumatic pontoon bridge and hope German artillery didn't destroy it before completion. He could try building a Bailey bridge, which would take even longer and require extensive foundation work on both banks. Or he could gamble on equipment that had never been tested under combat conditions. 300 of Steinman's experimental steel foam pontoons that had arrived at the Remagen depot 2 weeks earlier. The decision to use Steinman's design came down to pure desperation. Pergrin had watched German artillery destroy 2 attempted ferry operations in the previous 48 hours. He knew that any bridge construction would draw concentrated fire from German 88mm guns positioned in the hills east of the Rhine. The faster the bridge went up, the fewer men would die building it. Speed trumped everything else. On the morning of March 23rd, Pergrin's battalion began assembling what would become the first Steinman pontoon bridge under combat conditions. The engineering logs from that operation, preserved at the National Archives, read like a technical manual written under artillery fire, which is exactly what they were. 0530 hours. First pontoon sections positioned at West Bank. Current approximately 4 knots. Water temperature 42 degrees Fahrenheit. German artillery sporadic. Small arms fire from East Bank positions, suppressed by attached infantry. The assembly process bore no resemblance to traditional pontoon bridge construction. Instead of inflating rubber chambers and carefully positioning them with cranes, engineers simply manhandled the steel boxes into the water, 2 men per box, and clipped them together in the river itself. The current pushed the growing string of pontoons downstream, held in check by anchor cables attached to the West Bank. As each new section clipped on, the bridge extended another 8 feet toward the far bank. 0615 hours. 40 pontoons assembled. First treadway sections placed. German artillery increasing. 1 pontoon, holed by shrapnel, remains functional, foam providing adequate buoyancy. Crew continues assembly. The treadway system, the actual roadbed that vehicles would drive across, used standard M2 steel treadway sections, the same ones designed for Bailey bridges. These bolted directly to brackets welded onto Steinman's pontoons, eliminating the complex connection systems required for pneumatic pontoons. If a treadway section took a direct hit, engineers could unbolt the damaged piece and slide in a replacement without disturbing the pontoons underneath. 0745 hours. East Bank secured by infantry. Engineers beginning far bank connection. German counter-battery fire, increasing intensity. 1 casualty, fragment wound, evacuated. Bridge 70% complete. What normally required crane operators, specialized tools, and careful coordination was being done by combat engineers working in chest-deep water with nothing more than alignment pins and wrenches. The simplicity of Steinman's design meant that even under fire, even with cold-numbed fingers, soldiers could maintain assembly tempo. Drop the pin, move to the next pontoon, repeat. 0857 hours. Bridge complete. Total span 430 feet. Class 40 rated. First vehicles crossing at 0905 hours. Total assembly time 93 minutes from first pontoon to first vehicle crossing. 93 minutes. The operation that military doctrine said required 3 days had been executed in an hour and a half. By noon, Sherman tanks were crossing the Rhine at Remagen in continuous flow, 12 vehicles per hour, with supply trucks filling the gaps between armor. The bridge that military engineers had said was impossible had just saved the First Army's bridgehead and possibly shortened World War II in Europe by weeks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German artillery tried desperately to destroy the Steinman pontoon bridge. In the 72 hours following its completion, Wehrmacht gunners fired approximately 1,100 rounds at the Remagen crossing, a bombardment that included 155mm shells, 88mm direct fire, and even experimental radio-guided bombs dropped by Luftwaffe aircraft. The bridge took direct hits, treadway sections shattered, pontoons holed and flooded. 2 were blown completely off the bridge by near misses that sent geysers of Rhine water 40 feet into the air. And the bridge kept functioning. This was Steinman's design philosophy made manifest in combat. When a pneumatic pontoon takes a direct hit, it deflates and sinks, creating a gap in the bridge that requires hours to repair. When a Steinman foam-filled steel box took a hit, the worst-case scenario was a 20% loss of buoyancy that still left the pontoon functional. Engineers could patch holes with welded plates while the bridge remained in operation. If a pontoon was damaged beyond field repair, crews could pull the connecting pins, tow the damaged unit downstream, and slide in a replacement, all in under 20 minutes, without stopping vehicle traffic. The First Army engineering logs record 42 significant repairs to the Remagen pontoon bridge between March 23rd and March 31st. The bridge was never offline for more than 15 minutes at a time. During that same period, over 16,000 vehicles crossed from west to east bank, carrying 3 complete armoured divisions and their supporting logistics deep into Germany. The Rhine barrier, which had dominated Allied strategic planning for 2 years, had been breached and held open by a civilian engineer's crazy idea. News of the Remagen bridging success spread through Allied engineering units faster than official channels could distribute it. Within 2 weeks, Corps of Engineers depots across Europe were screaming for Steinman pontoons. Production ramped up with extraordinary speed because of the design's simplicity. Factories that had been building M1942 pneumatic pontoons could retool to Steinman boxes in under 3 weeks. By April 1945, 17 American manufacturing facilities were producing 3,000 Steinman pontoons per month. The impact cascaded across every river crossing in the European theatre's final weeks. When the 9th Army reached the Elbe River in mid-April, they bridged it in 2 hours and 17 minutes using Steinman pontoons. When Patton's 3rd Army crossed the main river near Würzburg, engineers assembled a 400-foot span in 88 minutes, while German artillery fired on their position. The bridges that had defined the pace of Allied advance, that had given Wehrmacht defenders days to prepare and counterattack, suddenly became minor obstacles cleared in the time it took an infantry company to secure both banks. German intelligence officers, captured after the war, testified that Allied bridging speed in March and April 1945 completely disrupted Wehrmacht defensive doctrine. Their entire river defense strategy assumed Allied armies would pause for 3 to 4 days at major water obstacles. When American forces began crossing in hours, German commanders couldn't reposition reserves fast enough to contest the bridgeheads. The war became a race that Germany couldn't win. The technical specifications of Steinman's pontoon design revealed why it succeeded where traditional systems failed. Each individual pontoon measured 8 feet long, 4 feet wide, and 30 inches deep. The hull was welded from quarter-inch steel plate in a simple rectangular box configuration. Total empty weight, 680 pounds, light enough for 4 men to maneuver without mechanical assistance, yet heavy enough to resist being thrown around by river current once in the water. Inside each box, expanded polyurethane foam filled approximately 70% of the interior volume. This foam, a relatively new material in 1944, had been developed for naval applications where watertight integrity was critical. The foam's closed-cell structure meant that even if the steel hull was punctured, water couldn't flood the entire pontoon. Each cubic foot of foam provided roughly 62 pounds of buoyancy when submerged. A single Steinman pontoon, even with the steel hull fully flooded, retained enough foam buoyancy to support approximately 400 pounds of vehicle weight. The connection system was equally straightforward. Each pontoon had 4 steel brackets welded to its corners, positioned precisely to align with brackets on adjacent pontoons. A 3/4-inch steel pin dropped through aligned brackets and was secured with a cotter pin that could be installed or removed with bare hands. No bolts, no welding, no specialized tools. A trained crew could connect 2 pontoons in under 45 seconds. Disconnection took less than 30 seconds. The genius of this simplicity became apparent when examining manufacturing logistics. Traditional M1942 pneumatic pontoons required specialized rubber vulcanization equipment, pneumatic valve assemblies imported from specific suppliers, and quality control, testing that included pressure testing every individual air chamber. Manufacturing capacity was limited to facilities with this specialized equipment. Production bottlenecks were common and persistent. Steinman pontoons could be built in any steel fabrication shop with basic welding equipment. The design called for straight welds along seams and corners, work that semi-skilled welders could execute reliably after minimal training. No complex curves, no tight tolerances, no precision machining. The foam filling process required slightly more care, but even this was straightforward. Foam came in two-part liquid form that mixed and expanded inside the sealed hull, curing to rigid foam in approximately 4 hours. By late April 1945, production numbers told the story. American industry produced 8,400 Steinman pontoons in April alone, more than triple the output of traditional pneumatic pontoons during the same period. Cost per unit had dropped to $39, including materials, labor, and transportation to European depots. The army was getting bridges faster and cheaper than at any point in military history. But production numbers don't capture the human experience of building these bridges under fire. That reality lived in the combat engineering units who did the actual work. The 291st Engineer Combat Battalion's after-action reports from the Remagen operation provide detailed insight into what pontoon bridge construction actually demanded from the men who performed it. First, there was the physical environment. The Rhine in March carried snowmelt from the Alps, with water temperatures hovering between 40 and 45 degrees Fahrenheit. Engineers worked in chest-deep water for hours at a time, manhandling 700-pound steel boxes while current pushed against them with relentless force. The risk of hypothermia was constant. Battalion medical logs record 23 cases of cold water, exposure requiring treatment during the Remagen bridge operation, including 4 severe cases where engineers had to be pulled from the water after losing motor control in their hands. Then there was the artillery. German gunners knew exactly where the bridge was and bracketed it with continuous fire. Engineers worked in the open, completely exposed, with no cover except the water itself. The psychological stress of working while knowing artillery rounds were incoming, hearing the whistle, waiting to see if this one would hit close enough to kill you, created trauma that persisted decades after the war ended. Post-war psychological studies of World War II combat engineers showed elevated rates of what we now recognize as PTSD compared to infantry riflemen. The constant exposure without the ability to take cover, fight back, or control the situation created a specific form of combat stress that many veterans never fully resolved. Interviews conducted in the 1980s with survivors of the Remagen bridge operation revealed consistent patterns: nightmares about drowning, acute anxiety around rivers or bridges, and persistent startle responses to sudden loud noises that mimicked incoming artillery. Yet the casualty statistics demonstrate that Steinman's design provided measurable protection through speed. The 291st Engineer Battalion suffered 9 casualties, including 3 killed, during the 93-minute Remagen bridge construction. For comparison, the 9th Army's attempted Rhine crossing at Wesel using traditional pneumatic pontoons took 4 hours and 17 minutes and resulted in 37 engineer casualties, including 11 killed. The correlation was stark. Every additional hour of bridge construction under fire multiplied casualties exponentially. Training made the difference between functional performance and catastrophic failure. Engineer battalions that had practiced with Steinman pontoons before combat deployment showed 40% faster assembly times and 60% fewer casualties than units using the equipment for the first time under fire. The Army's training infrastructure adapted rapidly. By March 1945, the engineer school at Fort Belvoir had integrated Steinman pontoon training into every combat engineer course, with mandatory rehearsals that continued until assembly procedures became automatic muscle memory. The standard training progression required engineer companies to build a complete 200-foot pontoon bridge in under 4 hours on their first attempt, under 3 hours by their 5th attempt, and under 2 hours by their 10th attempt. This represented a complete reversal of traditional engineering training philosophy, which emphasized careful, methodical construction over speed. The new doctrine recognized that in combat, speed saved lives, and anything that could be done quickly with adequate safety was preferable to slower methods that left soldiers exposed longer. Equipment maintenance under combat conditions posed challenges that peacetime testing never anticipated. Steinman pontoons were durable, but they weren't indestructible. Steel hulls developed cracks from stress, impact damage, and simple metal fatigue. Foam degraded when exposed to petroleum products, which meant pontoons used to transport fuel trucks required more frequent inspection and repair. The standard solution was brutal pragmatism. If a pontoon showed significant damage, pull it from service and replace it. No field repairs beyond welding obvious holes and pumping out flooded compartments. Forward engineer depots maintained reserve pontoon stocks specifically for rapid replacement. A typical engineer battalion supporting an armoured division kept 50 spare pontoons in immediate reserve, enough to replace an entire bridge section if necessary. This logistics tail consumed significant transport capacity, but commanders considered it essential. A bridge was only useful if it stayed functional, and functionality required readily available replacement parts. The Soviet Red Army, desperate for any advantage in their final push toward Berlin, obtained Steinman pontoon specifications through Allied cooperation in April 1945. Soviet engineers, accustomed to even more desperate improvisation than their American counterparts, embraced the design enthusiastically. They simplified it further, eliminating the foam filling entirely and relying solely on the sealed steel hull for buoyancy. This reduced manufacturing time but also reduced redundancy. Soviet pontoons worked well until they were holed, at which point they sank immediately. Soviet combat doctrine accepted this trade-off. Their engineering philosophy prioritized getting equipment to the front line as rapidly as possible, even if that equipment was less reliable than American or British equivalents. When Soviet forces bridged the Oder River during the final assault on Berlin, they used crude copies of Steinman pontoons, fabricated in Polish steel mills, with whatever materials were available. The bridges worked well enough to get 34 tanks across, which was all that mattered in April 1945. The British Army conducted formal evaluations of Steinman pontoons in April 1945, comparing them against their own Mark V pontoon equipment. British engineers appreciated the simplicity and speed, but had concerns about durability in sustained operations. Their solution was typically British. They refined Steinman's design with additional reinforcement brackets, improved welding specifications, and more sophisticated foam formulations that resisted petroleum degradation. The resulting British pontoon, Mark VII, introduced in 1946, was essentially a Steinman pontoon built to British manufacturing standards. This pattern of adoption and refinement repeated across Allied armies and continued into the post-war period. The fundamental concept, hollow steel boxes filled with buoyant material and connected by simple mechanical joints, proved so sound that it became the basis for virtually all military pontoon bridge development for the next 3 decades. When the war in Europe ended in May 1945, American forces had built over 350 major river crossings using Steinman pontoons. The bridges ranged from small tactical spans across 60-foot streams to major strategic crossings like Remagen that supported entire army groups. Total vehicle crossings, approximately 1.2 million, including tanks, trucks, artillery pieces, and support vehicles. The bridges that had threatened to become the choke points that delayed Allied victory had instead become minor obstacles cleared in hours. The Pacific Theatre saw limited use of Steinman pontoons primarily because most river crossings there involved different challenges. Coral reefs, tidal variations, and the need for amphibious operations meant that Pacific engineers relied more heavily on specialized landing craft and amphibious vehicles. However, Steinman pontoons did see service in the Philippines during the Luzon campaign, where they enabled rapid crossing of the Pampanga River and several smaller waterways that would have otherwise delayed MacArthur's drive toward Manila. John Steinman himself never witnessed his pontoons in combat. The army kept him in the United States throughout the war, primarily at Fort Belvoir, where he worked on continuous refinement of the design and training of engineer units. He received the Medal for Merit, the highest civilian decoration for wartime service, in a quiet ceremony in November 1945 that garnered almost no press attention. Steinman returned to Oklahoma in December 1945 and resumed building bridges for oil companies, largely forgotten by a nation celebrating more dramatic wartime achievements. The immediate post-war period saw military engineering undergo fundamental doctrinal revision based on lessons from Steinman pontoons and similar innovations. The U.S. Army's 1946 Field Manual for Engineer Operations codified new standards that reflected the reality. Bridge construction speed was as tactically important as firepower or maneuver. The manual specified that engineer units would train to build tactical bridges in under 2 hours regardless of width, that equipment would be designed for semi-skilled operation with minimal tools, and that logistics chains would prioritize bridge components as Class 1 supplies, the same priority level as ammunition and fuel. This represented a complete philosophical shift. In 1940, bridges were engineering projects requiring specialized experts and extensive time. By 1946, bridges were tactical obstacles that properly equipped units could clear rapidly as part of normal offensive operations. The difference wasn't just technological, it was conceptual. Steinman had proven that the right design could transform engineering from a limiting factor into an enabling capability. The Korean War, beginning in June 1950, validated this transformation immediately. When North Korean forces pushed south across the 38th parallel, they destroyed most bridges in their path, assuming this would slow American and South Korean counterattacks. U.S. Army engineer battalions, equipped with updated versions of Steinman pontoons and trained in rapid bridging doctrine, crossed the Han River near Seoul in under 3 hours during the September 1950 Incheon counteroffensive. North Korean defenders, who had positioned forces based on the assumption that river crossings would take days, found themselves outflanked before they could reposition. Throughout the Korean War's 3 years of mobile operations and static warfare, American engineers built over 600 tactical bridges using equipment directly descended from Steinman's 1944 design. The mountainous terrain and numerous rivers of the Korean peninsula made bridges absolutely critical to sustaining operations. The ability to bridge quickly meant that UN forces could maintain offensive pressure even as retreating forces destroyed infrastructure. The Vietnam War saw further evolution. The medium girder bridge system, adopted by US forces in 1965, used aluminum construction instead of steel, reducing individual component weight by nearly half while maintaining load-bearing capacity. But the underlying principles remained identical to Steinman's original concept: modular components, simple connections, rapid assembly by semi-skilled crews. American engineers built MGB bridges across the Mekong Delta's countless waterways, often under conditions that would have been impossible with traditional equipment. Soft mud banks, extreme heat, monsoon flooding, none of these prevented rapid bridge construction because the system was designed for improvisation and field adaptation. Soviet military engineering followed parallel development paths. The TMM mobile bridge system, introduced in 1958, mounted folding bridge sections on modified tank chassis for rapid deployment. 4 TMM vehicles could create a 40-meter span in under 15 minutes. The design philosophy came directly from World War II river crossing experience. Speed matters more than elegance, and anything that reduces assembly time determines whether a crossing succeeds under fire. Modern American military bridging equipment, the improved ribbon bridge introduced in 1985 and still in service today, uses modular bay sections carried on 5-ton trucks. A combat engineer company can deploy a 100-meter bridge in 30 minutes. Each bay section measures 6.7 meters long and connects to adjacent sections while floating on the water. The system can support Moan Abrams tanks weighing 62 tons, nearly double what World War II bridges handled. But examine the IRB's design principles, and Steinman's influence is unmistakable. Hollow aluminum construction with foam core for redundant buoyancy. Mechanical pin connections requiring only basic hand tools. Assembly procedures designed for semi-skilled operators working under stress. Modern military engineering has refined the technology, improved the materials, and increased the capacity, but it hasn't fundamentally changed the concept that a civilian engineer from Oklahoma proved in combat in March 1945. NATO standardization agreements established in the 1970s mandate that all member nations' military bridging equipment must be intercompatible. British, German, and American bridge components can connect to each other, allowing multinational engineering units to pool resources during operations. This interoperability doctrine stems directly from Rhine crossing experiences, where hybrid bridges successfully combined Allied and captured German equipment. The civilian engineering world adopted Steinman's principles more slowly, but just as thoroughly. After World War II, surplus military pontoons found second lives in disaster relief operations, rural infrastructure projects, and emergency bridge construction worldwide. The simplicity that made Steinman pontoons effective in combat made them ideal for civilian applications where specialized equipment and skilled crews were unavailable. Modern disaster relief organizations maintain pontoon bridge stockpiles, specifically for emergency deployment after earthquakes, floods, or infrastructure collapse. When the 2010 Haiti earthquake destroyed Port-au-Prince's road network, international relief teams airlifted modular bridge components directly descended from Steinman's design and had 3 major crossings operational within 72 hours. The 2011 Tohoku earthquake in Japan saw military engineers deploy modular bridges based on identical principles to restore coastal access roads. Military engineering schools worldwide still study the Remagen crossing as the definitive example of rapid tactical bridging under combat conditions. The U.S. Army Engineer School at Fort Leonard Wood teaches the operation to every combat engineer officer as a case study in how proper equipment and training enable tactical success. British Royal Engineers analyse the 93-minute assembly time as an example of optimal execution. The specific equipment has evolved, but the engineering philosophy remains identical to what Steinman demonstrated in 1945. John Steinman died in 1973 in Tulsa, Oklahoma, at the age of 70. His obituary in the Tulsa World ran 4 paragraphs and made no mention of his wartime contribution. Most Americans had never heard of him. The bridges that shortened World War II and saved thousands of lives bore no plaques with his name. There's no Steinman Memorial at Fort Belvoir, no engineer vessel named in his honor, no monument on the Rhine at Remagen. But if you've seen military engineers throw a bridge across a river in hours instead of days, you've seen his legacy. Every modular pontoon system in service with modern armies traces its conceptual lineage to a civilian engineer who refused to accept that traditional methods were the only methods. Every combat engineer who trains in rapid bridging doctrine learns principles that Steinman proved effective in March 1945. The 93 minutes that saved the Remagen bridgehead represented more than successful improvisation. It demonstrated that the right innovation at the right moment could transform tactical limitations into tactical advantages. Rivers had been barriers since armies first learned to march. Steinman didn't eliminate those barriers, but he made them crossable quickly enough that they stopped determining the outcome of campaigns. Wars are won by firepower, maneuver, and logistics. Sometimes they're also won by a civil engineer from Oklahoma who figured out that steel boxes filled with foam could work better than the pneumatic pontoons that military doctrine considered essential. The generals who planned river crossings got the recognition. The soldiers who fought across those bridges got the medals. But the bridges themselves, the unglamorous tools that made everything else possible, came from people who understood that solving problems matters more than following doctrine. Eisenhower said that the Remagen bridge crossing shortened the war in Europe by weeks, possibly months. He was talking about the Ludendorff Bridge capture, but the statement applies just as accurately to the pontoon bridge that replaced it. 75,000 American soldiers trapped on the wrong side of the Rhine needed that bridge. They needed it fast enough that German counterattacks couldn't crush the bridgehead. John Steinman gave them 93 minutes instead of 3 days. That difference, measured in hours saved and lives preserved, changed the war. Not dramatically, not obviously, but definitively. The Rhine barrier that had dominated Allied planning for 2 years became a minor obstacle cleared in an afternoon. Every river crossing afterward benefited from that precedent, from equipment improved by combat testing, from doctrine refined by success. The legacy wasn't glory or recognition. It was functional equipment that worked when soldiers needed it most. Modern military engineers still face the same fundamental challenges. How to move armies across water fast enough that momentum doesn't die at the riverbank. The equipment has evolved. The doctrine has been refined. But the essential problem remains identical to what Pergrin faced on the Rhine in March 1945. And when engineers need to solve that problem, they still reach for modular pontoons that clip together quickly, carry adequate load, and keep working even when damaged. The design that a civilian engineer sketched in 1944, built in Oklahoma steel mills, and tested under German artillery fire at Remagen, is still fundamentally sound 80 years later. That's not nostalgia. That's engineering done correctly the first time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.